There is one very important caveat to this picture. Recent research suggests that eternal inflationary models may be eternal in the future, but not in the past. They never stop, but they may have to start. I can't give you a definitive answer to this ultimate question because nobody yet knows. I can quote from André Linde's recent review of inflationary cosmology After Planck, 2013. In other words, there was a beginning for each part of the universe, and there will be an end for inflation at any particular point. But there will be no end for the evolution of the universe as a whole in the eternal inflation scenario. And at present, we do not know whether there was a single beginning of the evolution of the universe as a whole at some moment t equals 0, which was traditionally associated with the Big Bang. And so we reach the end. Defining the Big Bang as the initial hot, dense phase of our observable universe that gave rise to the CMB 380,000 years later, we understand what happened before. There was a period of inflationary expansion, which could have been driven by a scalar field in accord with the known laws of physics. That inflationary expansion is probably still going on somewhere, spawning an incalculable number of universes as we speak, and it will continue doing this forever. We live in an eternal universe, in which everything that can happen does happen. And we are one of the things that can happen. Did the whole universe have a beginning, an essential external cause in the spirit of Leibniz's God? We still don't know. Possibly there was a mother of all Big Bangs, and if so, we will certainly need a quantum theory of gravity to say anything more. What does this mean? The wonderful thing for me is that nobody knows, because the philosophical and indeed theological consequences of eternal inflation have not been widely debated and discussed. My hope is that in trying to summarize the issues, regrettably briefly and necessarily superficially in the television series, these ideas will be accessible to a wider audience and stimulate discussion. This is desirable and necessary, because ideas are the lifeblood of civilization, and societies assimilate ideas and become comfortable with their implications through understanding and debate. If eternal inflation is the correct description of our universe, it will be the artists, philosophers, theologians, novelists, and musicians, alongside the physicists, who explore its meaning. What does it mean if the existence of our universe is inevitable? What does it mean if we are not special in any way? What does it mean if our observable universe, with all its myriad galaxies and possibilities, is a vanishingly small leaf on an ever-expanding fractal tree of universes? What does it mean if you are because you have to be? I can't tell you. I can only ask, what does it mean to you? For small creatures such as we, the vastness is bearable only through love. Carl Sagan. But how on earth does a cell learn how to engulf another one and survive? How did endosymbiosis arise? A clue, and perhaps an even more significant bottleneck, may be found in another prerequisite for the Cambrian explosion, the eukaryotic cell. All multicellular organisms are made up of cells known as eukaryotes, cells with a nucleus and a host of specialized structures, each charged with performing specific tasks. The eukaryotic cells in every living thing look so similar that an alien biologist, knowing nothing about planet Earth, would immediately recognize that human eukaryotes are closely related to those from a blade of grass. The earliest known eukaryotic cells date from around 2 billion years ago. Beyond this, simpler cells known as prokaryotes were the only living things on the planet. Bacteria and archaea, the two single-celled kingdoms of life that still flourish today, are prokaryotes. They are simple in the sense that they lack the vast, specialized machinery of the eukaryotes, although, as we've seen, they do possess some vital and extremely complex abilities, photosynthesis being a very good example. The most striking difference between eukaryotes and prokaryotes is the eukaryote cell nucleus, which contains most of its DNA. In the story of evolution of life on Earth, however, it's the small amount of DNA stored outside the nucleus that's most revealing. Almost all eukaryotic cells contain structures called mitochondria. The word almost is used a lot in biology. Unlike physics, there always seem to be one or two exceptions that ruin sentences in books like this. Most biologists believe that even the eukaryotes that don't possess mitochondria did so at some point in the past, however, so we can take it that these structures are ubiquitous. Mitochondria are the power stations of the cell, and their job is to produce ATP. Around 80% of your energy comes from the ATP produced in mitochondria, and without them you certainly wouldn't exist. A clue as to their evolutionary origin is contained in their DNA, which is stored in loops and kept separate from the genetic material in the cell nucleus. Bacteria also store their DNA in loops, and this is not a coincidence. The mitochondria were once free-living bacteria. The obvious question is, how did the bacterial mitochondria get inside the cells of every complex organism on the planet? The answer is through endosymbiosis, just as for the chloroplasts. But there is not universal agreement on the detail, and the detail matters a great deal. What's not in question is that the mitochondria are bacterial in origin. The debate surrounds the nature of the original host cell. One camp of biologists believes that the host cell was already a eukaryote, which over many millions of years had evolved an ability called phagocytosis, the ability to ingest other cells. This is a traditional Darwinian explanation, one in which complex traits evolve gradually over time via mutations and natural selection. If this is true, then it's possible to view the eukaryotic cell as just another evolutionary innovation, albeit a very important one, that might crop up anywhere given enough time. The other possibility, which is favoured by many biologists, has different implications. The idea is that the swallowing of the protomitochondrial cell was the origin of the eukaryotic cell itself. There was no such thing as phagocytosis or the eukaryotic cell before this singular event, and this fateful encounter changed everything. Recent DNA evidence suggests that the host cell was probably an archaean, one of the two great prokaryotic domains. Somewhere in some primordial ocean, this simple prokaryote managed to swallow a bacterium, a trick that neither cell possessed before, and against terrific odds, the pair survived and multiplied. The archaean gained a huge advantage, a previously unimaginable energy supply from the bacterium's sophisticated ATP factory. The bacterium also gained an advantage. It was protected, and over eons could specialize and concentrate entirely on producing energy for its host. If this theory is correct, the origin of complex life on Earth was a complete accident. Without access to the energy supply from the mitochondria, all the complexities of the eukaryotic cell, which are absolutely necessary for complex multicellular life, would never have evolved. Earth would be a living planet today, but a planet of prokaryotes, and certainly not home to a civilization. I cannot tell you which of these two theories is true. If it were obvious, then all academic biologists would agree. But my impression is that the fateful encounter is currently the more widely accepted theory. And if it is correct, then this has very important consequences for estimating the probability of the evolution of intelligent life. Eukaryotes are absolutely essential for intelligence. There is no biologist who would suggest that the prokaryotes, for all their ingenuity in developing photosynthesis and mitochondrial machinery, would have managed to construct radio telescopes given enough time and a following wind. Without eukaryotes, there would be only slime. I think these are very important points to consider in the Drake equation. If it is correct that at least two of the necessary foundations for the emergence of complex multicellular life on Earth arose from barely credible accidents, then they might be seen as potential bottlenecks in the evolution of intelligence elsewhere in the Milky Way. So where are we in our attempt to estimate the chances that, given the origin of life on a planet, intelligence will arise. This is where we move from science to speculation and opinion. And with these caveats, let me give you my personal view. Given the eukaryotic cell and an oxygen atmosphere, life on Earth became diverse and complex relatively quickly. It's almost certainly no coincidence that the Cambrian explosion followed soon after a rapid rise in the oxygen content of the atmosphere. Whether it's possible to claim that intelligence on the scale necessary to build a civilization is likely given the right biological building blocks in enough time, 500 million years, let's say, is another question. We simply don't know, and the very specific conditions in the African Rift Valley that led to the emergence of early modern humans only 250,000 years ago might suggest that civilization-level intelligence is a rare development, even given animals as sophisticated as primates, never mind a eukaryote and an oxygen atmosphere. An optimist would assert that there are billions of potential homes for life in the Milky Way, and that since life emerged on Earth pretty much as soon as it could at the end of the violence of the Hadean, then the Milky Way must be teeming with life, and therefore civilizations. I would agree that the Milky Way must be teeming with life. I think there's a sense of chemical inevitability about it. Even accepting this line of argument, however, a pessimist would surely point to the evolution of the eukaryotic cell and oxygenic photosynthesis as being potential bottlenecks. On Earth, it took life over 3 billion years to get to the eve of the Cambrian. That's 3 billion years of planetary stability, a quarter of the age of the universe. If just one of the necessary steps, the fateful encounter, let's say, was at the fortunate end of a probability distribution, then one can easily imagine that the 20 billion Earth-like worlds in the Milky Way could all be covered in prokaryotic slime. A living galaxy, yes, but a galaxy filled with intelligence? Given what we know about the ascent from prokaryote to civilization on Earth, I'm not so sure. Let's take one final journey back to Green Bank in 1961. Drake and his colleagues, with far less evidence than we have today, concluded that our galaxy seems remarkably conducive to life, full of Earth-like worlds warmed by the glow of benign stars. They too believed that a good fraction of these billions of worlds must be home to life, and given that Darwin's law of evolution by natural selection must apply across the universe, they concluded that intelligence must have emerged on at least some of these planets. As I've argued above, I'm not so sure about intelligence, but we must at least consider the possibility that potential evolutionary bottlenecks like the eukaryotic cell and oxygenic photosynthesis aren't as bad as they might appear. In this case, the final term in the Drake equation becomes all-important. Perhaps it is L, the lifetime of civilizations, that is the fundamental reason for the Great Silence. This is a sobering thought. The reason we've made no contact with anyone is not because of a lack of stars, or planets, or living things. It's because of the inbuilt and unavoidable stupidity of intelligent beings. This might seem a bit strong, but it's a view shared at Green Bank by Manhattan Project veteran Philip Morrison. Morrison was intimately involved in the design and development of the first atomic bomb, and he helped load Little Boy onto Enola Gay, destined for Hiroshima. The fact that human beings had deployed a potentially civilization-destroying weapon twice against civilian targets, and that Morrison had personally loaded one of the bombs, must have never left him. And on the eve of the Cuban Missile Crisis, it must have seemed likely that we would do it again on a much grander scale. Drake realized this as well, which is certainly one of the reasons why he introduced the time that a technological civilization can endure into his equation. We can, after all, only communicate with nearby civilizations if they exist at the same time as us. This is a possible resolution to the Fermi paradox. Civilizations inevitably blow themselves up soon after acquiring radio technology, and therefore the Milky Way will remain forever silent apart from the briefest, non-overlapping flickers of intelligence. This might seem like a solipsistic conceit. How can we possibly assume that human stupidity is universal? We can't, of course. But just as for the biological arguments we made against the inevitable emergence of complex life on an otherwise living world, we only have the Earth as a guide, and extrapolating from our own experience is the best we can do. On Earth, Rutherford discovered the atomic nucleus in 1911, and we destroyed 2 cities and killed over 200,000 of our fellow human beings with nuclear technology 34 years later. About 17 years after that, having seen the devastation nuclear weapons can cause, Khrushchev and Kennedy came close to ending it all. And to this day, we don't know how close we came to eliminating the fruits of almost 4 billion years of evolution. Here on Earth, it appears that sanity, perspective, and an appreciation of the rarity and value of civilization emerges after and not before the capability to build big bombs. We have the bombs, but I don't think enough of us have the rest. Why should other young civilizations be any different? If this is the reason for the great silence, then I suppose we might take comfort in the fact that we are not the only idiots to have existed in the Milky Way. But that's the coldest comfort I can imagine. The above might be seen as a naive rant, of course. One could argue that mutually assured destruction, the guiding principle of the Cold War, did act to stabilize our civilization and is still doing so today. Perhaps no intelligent beings will knowingly destroy their civilization, which is what global nuclear war on Earth would surely do. After all, Kennedy and Khrushchev ultimately took this view. Similarly, one assumes that the submersion of Miami and Norwich by rising sea levels would silence the so-called climate change skeptics, I'd call them something different, and trigger a change of policy that will avert catastrophic civilization-threatening climate change in good time. It seems to me, however, that a small planet such as Earth cannot continue to support an expanding and flourishing civilization without a major change in the way we view ourselves. The division into hundreds of countries, whose borders and interests are defined by imagined local differences and arbitrary religious dogma, both of which are utterly irrelevant and meaningless on a galactic scale, must surely be addressed if we are to confront global problems such as mutually assured destruction, asteroid threats, climate change, pandemic disease, and who knows what else, and flourish beyond the 21st century. The very fact that the preceding sentence sounds hopelessly utopian might provide a plausible answer to the great silence. So, are we alone? What, then, is the range of estimates for the number of civilizations in the Milky Way, given the limited evidence we have at our disposal? During the filming of Human Universe, Frank Drake told me that the Green Bank meeting came up with a number of around 10,000, and he sees no reason to change that estimate. This would be wonderful, and makes the search for signals from these civilizations one of the great scientific quests of the 21st century. I strongly support SETI, because contact with just one alien civilization would be the greatest discovery of all time, and it's worth the investment on that basis alone. There is, however, one piece of evidence that might suggest a more lonely position for us on our little home world. In 1966, the mathematician and polymath John von Neumann published a series of lectures entitled Theory of Self-Reproducing Automata, in which he analyzed in great detail the possibility of constructing machines capable of building copies of themselves. Such machines exist in nature, of course. All living things do this routinely. In principle, therefore, one might imagine a sufficiently advanced civilization building a self-replicating von Neumann space probe and launching it out to explore the galaxy. On reaching a solar system, the probe would mine the planets, moons, and asteroids, extracting the materials necessary to build one or more copies of itself. The newly minted probes would launch themselves out to neighboring solar systems and repeat the process, spreading across the Milky Way. Even given the vast distances between the stars, computer models assuming currently envisioned rocketry technology suggest that such a strategy could result in the exploration of the entire Milky Way galaxy within 1 million years. Science fiction? It certainly sounds like it. But if there's no objection in principle to the construction of a von Neumann probe, then one has to develop an argument as to why we don't see any. The reason that this is difficult to do is due to timescales. The Milky Way has been capable of supporting life for over 10,000 million years. It is possible to envisage many millions of civilizations rising and falling over such vast expanses of time, and if only one had developed a successful von Neumann probe, then the galaxy should be filled with its progeny. There should be at least one von Neumann probe operating in our solar system today. Carl Sagan and the astronomer William Newman noticed a flaw in this line of argument. If the probes multiply exponentially and unchecked, then one can show that they consume the resources of the entire galaxy relatively quickly, and we'd certainly have noticed that, or more accurately, we wouldn't be here to notice that. Sagan reasoned that this obvious risk would be sufficient to prevent any civilization intelligent enough to build von Neumann probes from actually doing so. They would be doomsday machines. Other astronomers have countered that it wouldn't be beyond the wit of such an advanced intellect to build in some fail-safe mechanism that guaranteed, for example, only one probe per solar system, or a finite lifetime for each probe. Others have argued that there may indeed be a von Neumann probe operating in our solar system today with appropriate fail-safe mechanisms installed to stop it eating everything. If such a probe were relatively small, perhaps sitting amongst the asteroids or even the Kuiper belt of icy comets beyond the orbit of Neptune, then we'd almost certainly be unaware of its presence. Von Neumann probes wouldn't be the only signatures of ultra-advanced civilizations. Imagine a civilization many millions of years ahead of us, carrying out engineering projects on a galactic scale. Imagine interstellar starships, or great space colonies constructed in otherwise uninhabitable solar systems. Why not? What signature will we leave on the sky if we survive and prosper that long? None of these questions is trivial, because the sheer immensity of the timescales available for life to evolve in the Milky Way galaxy forces us to consider them. Why should we be the most advanced civilization in the galaxy when we've only been building spacecraft for half a century in a 13-billion-year-old universe? I don't have an answer to this. It bothers me. Perhaps the distances between the stars are indeed too great, or perhaps there are insurmountable difficulties in building self-replicating machines or starships. But I can't think what they might be. I am tempted, therefore, to make the following argument for the purposes of debate. I think that advanced spacefaring civilizations are extremely rare, not because of astronomy, but because of biology. I think the fact that it took almost 4 billion years for a civilization to appear on Earth is important. This is a third of the age of the universe, which is a very long time. Coupled with the remarkable contingency of the evolution of the eukaryotic cell and oxygenic photosynthesis, not to mention the 500 million years from the Cambrian explosion to the very recent emergence of Homo sapiens and civilization, I think this implies that technological civilizations are stupendously rare, colossally fortuitous accidents that happen on average in much fewer than 1 in every 200 billion solar systems. This is my resolution to the Fermi paradox. We are the first civilization to emerge in the Milky Way, and we are alone. That is my opinion, and given our cavalier disregard for our own safety, it terrifies me. What do you think?
But why, some say, the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why 35 years ago fly the Atlantic? We choose to go to the moon.
President John F. Kennedy. Feel if his epitaph read, John Young, the ultimate explorer. Young smiled and in a test pilot's drawl replied, I'd feel sorry for the guy who wrote it. Young was, and still is, a hero of mine. My first vivid memory of live space exploration was watching Space Shuttle Columbia climb on a tower of bright vapor into a blue Cape sky on the 12th of April 1981. It was midday in Manchester, the Easter holidays, and I was 13 years old. Because of a 2-day launch delay, Columbia's test flight took place precisely 20 years to the day after Yuri Gagarin made his black-and-white voyage into orbit on the 12th of April 1961. But Young and his co-pilot Bob Crippen, in their orange spacesuits, were astronauts from the color age, the future, as distant from the Russian hero as gleaming white-winged Columbia was from Vostok 1. Equidistant from both was Apollo, which Young flew to the moon. Twice. It was the age of optimism, the age of wonder, the golden age when the ape went into space, when unflappable aviator Young, whose pulse rate did not increase during the launch of NASA's only manned spacecraft ever to have flown without an unmanned test flight, piloted Columbia back for a flawless manual landing at Edwards Air Force Base 2 days later. He turned to Crippen and said, "We're not too far away. The human race isn't. From going to the stars." In 2014, the stars feel further away than they did in 1981. The International Space Station is a wonderful piece of engineering that has allowed us to learn how to live and work in near-Earth orbit, but it is no closer to the stars than Columbia. Its construction is no mean achievement. One of the most important things to realize about engineering at the edge is that the only way to learn is to actually do it. You can't think your way into space, you have to fly there. But I can't help but feel, in the words of Billy Bragg, that the space race is over and we've all grown up too soon. It was different in Gagarin's day. Nobody's born to be a spaceman. We're apes, honed by natural selection to operate in the Great Rift Valley. Gagarin's father was a carpenter, and his mother was a milkmaid. Both worked on a collective farm. Gagarin's first job at the age of 16 was in a steel mill. But after showing an aptitude for flight as an air cadet, he joined the military when 21 and was posted to the 1st Chekhovsk Air Force Pilot School in Orenburg. Rising through the ranks, he made a name for himself as a skilled and intelligent aviator, and in early 1960 he was chosen along with 19 other elite pilots for the newly established space program. Standing just 5 foot 2 inches tall, Gagarin had the right stuff, and was perfect for the tiny Vostok spacecraft, whose single-seat crew compartment was only 2.3 meters in external diameter. After a year of training, Nikolai Kamenin, head of the cosmonaut program, chose Gagarin ahead of his rival German Titov, just 4 days before the flight. The history books are filled with the names of great men and women whose presence in the collective memory of humanity was assured by the slimmest of margins. Gagarin, alongside Armstrong, will be remembered for as long as there are humans in the cosmos. The name of the equally brilliant Titov, Russia's second cosmonaut, has faded away. Gagarin's flight was a true journey into the unknown. Strapped on top of the Vostok K rocket, which flew 13 times and made it into space on 11 occasions, the 27-year-old performed like a true test pilot. Despite a 2-hour delay during which every component of the spacecraft hatch was taken apart and rebuilt while Gagarin remained strapped into his seat, his heart rate was recorded at 64 beats per minute just before launch. This is not to say that Gagarin wasn't fully aware of what he was about to do. Before boarding, Gagarin made one of the great speeches of the age. "Dear friends, both known and unknown to me, fellow Russians and people of all countries and continents, in a few minutes, a mighty spaceship will carry me into the faraway expanses of space. What can I say to you in these last minutes before the start? At this instant, the whole of my life seems to be condensed into one wonderful moment. Everything I have experienced and done till now has been in preparation for this moment. You must realize that it is hard to express my feeling now that the test for which we have been training long and passionately is at hand. I don't have to tell you what I felt when it was suggested that I should make this flight, the first in history. Was it joy? No, it was something more than that. Pride? No, it was not just pride. I felt great happiness. To be the first to enter the cosmos, to engage single-handed in an unprecedented duel with nature. Could anyone dream of anything greater than that? But immediately after that, I thought of the tremendous responsibility I bore, to be the first to do what generations of people had dreamed of, to be the first to pave the way into space for mankind. This responsibility is not toward one person, not toward a few dozen, not toward a group. It is a responsibility toward all mankind, toward its present and its future. Am I happy as I set off on this space flight? Of course I'm happy. After all, in all times and epochs, the greatest happiness for man has been to take part in new discoveries. It is a matter of minutes now before the start. I say to you, until we meet again, dear friends, just as people say to each other when setting out on a long journey. I would like very much to embrace you all, people known and unknown to me, close friends and strangers alike. See you soon. It's too easy to attach trite labels to human actions, magnificent, horrific, and everything in between, based on a simplified view of their causes. One can argue that the rockets carried aloft the egos of the superpowers alongside the astronauts, and this is surely right. But Gagarin spoke these words, and I challenge anyone to read them and not detect sincerity. All our actions mask a morass of motivations, worthy and less so. And the greatest human adventures are no less noble for that. At 9:07 a.m. local time, Gagarin blasted off from Baikonur Cosmodrome in Kazakhstan, as every Russian cosmonaut has done since. Within 10 minutes, he was orbiting Earth at an altitude of 380 kilometers. His route took him across the Siberian wastes and the Pacific Ocean above the Hawaiian Islands, past the tip of South America and into the South Atlantic, where he was greeted by a second sunrise before a 42-second de-orbit burn over the Angolan coast slowed Vostok 1 into a parabolic orbit and an 8G deceleration inside Earth's thickening atmosphere. The journey once around his home world took 1 hour and 48 minutes. Gagarin ejected from the capsule 7 kilometers above ground, and, as planned, cosmonaut and spacecraft completed the final descent apart. Gliding back to Earth by parachute, Gagarin landed 280 kilometers away from the intended landing site near the Russian city of Engels. Dressed in orange spacesuit and white helmet, a farmer and his daughter bore sole witness to his historic return. When they saw me in my spacesuit and the parachute dragging alongside as I walked, they started to back away in fear, recollected Gagarin later. I told them, "Don't be afraid. I am a Soviet citizen like you, who has descended from space, and I must find a telephone to call Moscow." Primates appeared relatively recently in the history of life on Earth. Studies of mitochondrial DNA suggest the Strepsirrhini suborder, containing the ancestors of Madagascar's lemurs, diverged from our own Haplorhini suborder approximately 64 million years ago, which implies that a common ancestor was present before this time, but not a great deal earlier. The first complete primate fossil found to date is that of a tree-dwelling creature known as Archicebus achilles, dated at 55 million years old. Discovered in the fossil beds of central China in 2013, this tiny creature would have been no bigger than a human hand, making it not only the oldest, but also one of the smallest known primates. Our family, known as the Hominidae, or more commonly the great apes, share a common ancestor with Old World monkeys around 25 million years ago. The road out of Addis towards the 3,000-meter Guasa Plateau is excellent to a point, and then not excellent. The scenery, on the other hand, improves with altitude. Golden grasses illuminated by shifting lambent light through dark clouds cling to near vertical mountainsides framing pristine villages along the high valley floors. It is fresh, cold, and insectless on the peaks above the rift, a place to drink tea and eat shiro, a spiced Ethiopian stew of chickpeas and lentils. After a night in the cold but magnificently desolate Guasa Community Lodge, we set off at dawn to intercept the gelada baboons on their way back to their caves and ledges from early morning foraging expeditions on the higher slopes. The gelada baboons are a species of Old World monkey found only in the Ethiopian highlands. They're the only surviving species of the genus Theropithecus that once thrived across Africa and into southern Europe and India. The males in particular are powerful, long-haired animals, weighing over 20 kilograms, with a bright red flash of skin on their white chests. I was told not to look them in the eye, so I didn't. 50,000 years ago, as our planet emerged from the last ice age, the gelada retreated into the highlands above the rift, where they still live, uniquely among extant primates, as graminivores, on a diet made up almost entirely of the tough, high-altitude grasses and occasional herbs. They approach with nonchalant agility in small groups, which reflect the most complex social structure of any non-human primate. Most of the groups I saw contained 1 or 2 males and perhaps 8 or 10 females and their young. These are referred to as reproductive units, and clearly defined hierarchies exist within them. Females usually remain in the same unit for life, but males move between them every 4 or 5 years. There are also male-only units of 10 or 15 individuals. These social units are arranged into higher groupings known as bands, herds, and communities. The community we encountered numbered several hundred individuals who wandered past in their little tribes, females and young pausing to eat, groom and play, whilst the larger males eyed us closely. Despite the 25 million year separation in evolutionary time, the gelada are very easy to anthropomorphize, especially from a vantage point amongst them, probably because their behavior seems reminiscent of our own, and their babies are cute. Like us, they spend most of their time on the ground and operate in social groups. Some researchers familiar with the geladas claim they exhibit the most sophisticated communication behavior of any non-human primate, employing gestures and a range of different vocalizations, strung together into sequences communicating reassurance, appeasement, solicitation, aggression, and defense. For all their sophistication, however, the gelada are a long way from possessing anything more complex than the simplest of human characteristics and abilities. This is, of course, an utterly obvious observation. They are monkeys. But what isn't obvious is why. The gelada separated from our common ancestor at the same time. But that self-evident statement leads to a deeper question. What is it that happened to our ancestors during those 25 million years that led us to the stars and left them on the hillsides of the Guasa Plateau eating grass? I am an aviation geek. I love aircraft. As I set off to film the African scenes for 8-Man Spaceman, I noticed that the Ethiopian Airlines Boeing 787 I boarded at London Heathrow bound for Addis Ababa, registration ETAOS, was named Lucy. On the morning of the 24th of November 1974, Donald Johansen and a team of archaeologists were searching for bone fragments at a site near the Awash River in Ethiopia. The area was known to be a site rich in rare hominid fossils, but on that particular morning, Johansen and his graduate student Tom Gray found little to inspire them. As is often the way in science, however, a dash of serendipity coupled with an experienced scientist who understands how to increase the chances of receiving its benefits made a seminal contribution to the understanding of human evolution. Johansen shouldn't even have been there. He had planned to spend time back at the camp updating his field notes. But as they prepared to leave, Johansen decided to wander over to a previously excavated gully and have one last look. Even though they'd surveyed the area before, this time Johansen's eye was drawn to something lying partially hidden on the slope. Closer inspection revealed it to be an arm bone, and a host of other skeletal fragments, a piece of skull, a thigh bone, vertebra, ribs, and jaw, all emerged from the ground, and crucially, they were all part of a single female skeleton. The find triggered a 3-week excavation, during which every last scrap of fossil AL288-1 was recovered. They named it Lucy, after track 3, side 1 of Sgt. Pepper's Lonely Hearts Club Band, because this was 1974 and they played it a lot on their tape recorder. Home taping kills music, they used to say back then, but it also names airliners. Lucy lived 3.2 million years ago in the open savanna of Ethiopia's Afar Depression. Standing just over 1 meter tall and weighing less than 30 kilograms, she would have looked more ape-like than a human. Her brain was small, about 1/3 of the size of a modern human's and not much larger than a chimpanzee's. The anatomy of her knee, the curve of her spine, and the length of her leg bones suggest that Lucy regularly walked upright on 2 legs, although there are a handful of scientists who would disagree. What is generally agreed upon, however, is that Lucy was a member of the extinct hominin species Australopithecus afarensis, and she was either one of our direct ancestors or very closely related to them. Her bipedalism was probably an evolutionary adaptation caused by climate change in the rift. As the number of trees reduced, and the landscape became more savanna-like, the arboreal existence of our more distant ancestors became less favoured, and the increasing distances between trees selected for Australopithecus's upright gait made travel across the ground more efficient. In Who Speaks for Earth, the 13th chapter of Carl Sagan's Cosmos, there are 2 pictures set side by side. One is of footprints covered by volcanic ash 3.7 million years ago near Laetoli in Tanzania, probably made by an Australopithecus afarensis like Lucy. Some 400,000 kilometers away, and 3.7 million years later, another hominin footprint was left in the dust of the Sea of Tranquility. Together, they speak eloquently of our unlikely, magnificent ascent from the Rift Valley to the stars. The timescale is ridiculously small, less than 0.1% of the period of time during which life has existed on Earth. Lucy was little more than an upright chimpanzee, an animal, a genetic survival machine. We bring art, science, literature, and meaning to the Earth. We are a world away, and yet separated by the blink of an eye. Our obligation to survive is owed not just to ourselves, but also to that cosmos, ancient and vast, from which we spring, wrote Sagan. I'd like to add that we owe it to Lucy as well. Before astrology was consigned to the status of trifling funfair entertainment by science, it was believed that the position of the planets against the distant stars had a profound effect on people's daily lives. If you don't know what the stars or planets actually are, this is at least within the bounds of reason. But as our understanding of physics improved, so it became clear that there's no way that the position of a distant planet relative to the fixed stars can have any effect on the behavior of a human being on the surface of the Earth. The planets can and do affect the Earth's motion through the solar system over timescales far greater than those of human lifetimes, though. And recent research suggests that long-term changes in Earth's orientation and orbit may have played a crucial role in hominid evolution. Polaris is a true giant, almost 50 times the diameter of our Sun. It is also a Cepheid variable, one of the valuable standard candles upon which the astronomical distance scale rests. At a distance of only 434 light-years, it's both the closest Cepheid and one of the brighter stars in the sky, dominating the constellation Ursa Minor. Polaris also happens to be aligned directly with the Earth's spin axis, and this special position on the celestial North Pole makes it invaluable to navigators. As the Earth spins on its axis, Polaris sits serenely as all other stars rotate around it. At any point in the northern hemisphere, your latitude is the angle between Polaris and the horizon, 0 degrees north at the equator, where Polaris is on the horizon, and 90 degrees north at the pole, where Polaris is directly overhead. As viewed from Oldham, Lancashire, UK, Polaris sits at an angle of 53.54 degrees above the horizon. Christopher Columbus and Ferdinand Magellan relied on Polaris as they crossed the oceans and explored new worlds. Perhaps more surprisingly, on board Apollo 8, Jim Lovell carried a sextant as a backup navigational device. Designed by the MIT Instrument Laboratory in Cambridge, Massachusetts, it may not have looked traditional, but it operated in exactly the same manner as the one constructed by instrument maker John Bird in 1757. Polaris was one of Apollo's key navigational stars. It was paired with Gamma Cassiopeiae on Lovell's charts, which was known in Apollo jargon as Navi. The name was coined by Gus Grissom on Apollo 1 as a prank. It was his middle name, Ivan, backwards. Two other navigational stars, Gamma Velorum and Iota Ursa Major, were named Rhaegor after Roger Chaffee and Denoques after Ed White II. Using the stars for navigation might seem hopelessly old-fashioned, but if you think about it for a moment, you'll realize that there's no other way that a spacecraft in deep space can orient itself, other than relative to the fixed stars on the celestial sphere. A spacecraft will often shift its position relative to the stars, but on Earth things feel different because our orbit around the Sun is relatively stable from year to year. There are wobbles on relatively short timescales associated with changes in the speed of Earth's rotation, and these lead to the insertion of leap seconds to keep our atomic clocks synchronized with the heavens. Between 1972 and 1979, 9 leap seconds had to be inserted, whilst none was needed between the beginning of 1999 and the end of 2005. Earth's rotation rate is noticeably chaotic when compared to the accuracy of atomic clocks. The largest short-term contribution to changes in Earth's rotation comes from the gravitational influence of the Moon, which acts to slow down the rate of spin by around 2.3 milliseconds per century due to friction between the tidal bulges in the oceans and the rotating solid Earth beneath. But there are also longer-term changes. The most pronounced of these is known as axial precession, or more commonly, the precession of the equinoxes. The Earth spins on its axis like a gyroscope, and because it spins, it bulges out at the equator. Because the Earth isn't a perfect sphere, the gravitational influence of the Sun and Moon exerts a torque on the Earth that causes its spin axis to sweep round in a circle once every 26,000 years. This is not subtle, because the spin axis itself is tilted at 23 degrees relative to the plane of Earth's orbit, and precession therefore has a large effect on the night sky that was first documented by the Greek astronomer Hipparchus around 150 BCE. Precession manifests itself as a shift in the position of the celestial pole relative to the fixed stars. There will come a time in the not-too-distant future when Polaris will no longer sit above the celestial North Pole, as our spin axis traces out a circle in the sky. In about 3,000 years' time, navigators of the future will rely on Gamma Cephei as a backup for their GPS systems as they sail across the seas of our planet, and in 8,000 years it will be the bright star Deneb. The identity of the North Star has altered many times throughout human history. As the Egyptians finished building the Great Pyramid of Giza in 2560 BCE, Alpha Draconis lay closest to the celestial pole. 2,500 years later, as the Romans did things for us, Cocab, the second brightest star in Ursa Minor, and its neighbour Ferchard were known as the guardians of the pole. Precession, therefore, affects navigation. But more importantly, it also affects our climate. The 23-degree tilt of Earth's spin axis is responsible for the seasons. Summer in the northern hemisphere occurs when the North Pole is tilted towards the Sun, leading to constant daylight within the Arctic Circle. Half a year later, and the geometry is reversed, with the South Pole receiving 24-hour daylight and the southern hemisphere experiencing summer. Precession alone would have no effect on the climate if the Earth's orbit were a perfect circle. But it isn't. It's elliptical, with the Sun at one focus. At the turn of the 21st century, it happens to be the case that the Earth is at its closest approach to the Sun, known as perihelion, in January, just after the winter solstice, when the North Pole is pointing away from the Sun. This makes northern winters slightly milder than they would otherwise be, because the Earth receives a little bit more solar radiation during the northern winter. In around 10,000 years' time, however, precession will have carried the Earth's spin axis around by a half turn, and it will be the North Pole that points towards the Sun at perihelion, making northern hemisphere summers slightly warmer and winters cooler. The more elliptical the Earth's orbit, the more pronounced this effect. This is where things get a little more complicated, but it's the complication that matters for our story. The planets are significantly further away than the Moon, but also significantly more massive. and their constantly shifting positions induce periodic changes to our orbit over long timescales. Jupiter has the most pronounced effect due to its large mass and relative proximity. The largest of these changes occurs on a timescale of 400,000 years. Picture the Earth's orbit becoming periodically more elliptical and more circular, stretching back and forth with a period of 400,000 years. This oscillation modulates the effect of precession on the climate. At the times when the Earth's orbit is at its most elliptical, the changes due to precession will be at their most pronounced. This effect is known as astronomical or orbital forcing of the climate. There are many such resonances in Earth's orbit. Another important change in the eccentricity of the ellipse occurs every 100,000 years. Furthermore, the tilt of the axis itself swings back and forth between around 22 and 25 degrees on a 41,000-year cycle. The whole solar system is like a giant bell, ringing with many hundreds of harmonics, driven by the gravitational interactions between the Sun, planets, and moons. Over many thousands of years, these shifts in the Earth's orbit and orientation relative to the Sun have led to dramatic changes in climate and are certainly one of the key mechanisms that drive the Earth into and out of ice ages. It is perhaps obvious that these long-term shifts in climate should have had an effect on the evolution of life. Ice ages present a significant challenge to animals and plants, and this will provoke an evolutionary response via natural selection. More surprisingly, recent research has suggested a direct link between precession, the 400,000-year eccentricity cycle, and the evolution of early modern humans. The Great Rift Valley. Evocative words that immediately suggest origins. There are many reasons I love visiting Ethiopia. I love the people. I love the food. I love the high-altitude freshness of Addis. I love the mountains and valleys and high plains. I even loved visiting Erta Ale, the legendary shield volcano at the Afar triple junction known as the Gateway to Hell, although I probably won't do it again. But I also love an idea. It's impossible to visit this ancient country and not catch a glimpse in your peripheral vision of a chain of ghosts stretching back 10,000 generations, because it is firmly embedded in popular culture that we came from here. Every one of us is related to someone who lived in Ethiopia hundreds of thousands of years ago. It is the Garden of Eden, the place where humanity began. What popular culture has yet to assimilate, however, is the fortuitous and precarious nature of the ascent of man. When I was growing up, I remember talk of the missing link, that elusive fossil that would tie us definitively to our ape-like ancestors. When I started school, DNA sequencing was not yet invented, and Lucy hadn't been unearthed. Today, we have a significantly more complete view of how Australopithecines like Lucy are related to modern humans, and whilst the details are still debated and new evidence is continually updating the standard model of hominin evolution, it's now possible to tell the broad sweep of the story in some detail. The members of our human evolutionary family are referred to as hominins. The split between hominins and the ancestor of the chimpanzee occurred at some point before 5 million years ago in Africa, and by 4 million years ago Australopithecus afarensis, Lucy, was present. Their brain size was approximately 500 cc, around the same as a chimpanzee, and less than 1/3 that of a modern human. Around 1.8 million years ago, there was a step change in both brain size and the number of hominin species in the East African Rift. Several species of our genus Homo appeared, including Homo habilis and Homo erectus. They lived for a time alongside other species, including several Australopithecines and a genus known as Paranthropus. There are anthropologists who prefer to classify Paranthropus as a different species of Australopithecus. I make this point not to be confusing, but to highlight an important fact. The study of hominin evolution is a difficult area, and it's not surprising that there are ongoing debates about the classification of 2-million-year-old fossils and DNA sequences. What's important for our story, however, and what nobody disputes, is that there seems to have been a jump in both brain size and the number of species of hominins in the Rift Valley region around 1.8 million years ago. By around 1.4 million years ago, only one of these species had survived, Homo erectus, with a brain size of 1000 cc. The next milestone is the appearance of Homo heidelbergensis, around 800,000 years ago. Homo heidelbergensis is generally accepted to be the ancestor of Homo sapiens and the Neanderthals who lived alongside us in Europe until around 45,000 years ago, and possibly later. Homo heidelbergensis represented another jump in brain size, up to around 1400 cc, which is close to that of modern humans. In the late 1960s and early 1970s, two hominin skulls were found near the Omo River in Ethiopia. Known as Omo 1 and Omo 2, argon dating of the volcanic sediments around the level they were found dates them at 195,000 plus or minus 5,000 years old. These are the earliest fossilized remains to have been identified as Homo sapiens. The interesting question is what caused these rapid increases in brain size, driving hominin intelligence from the chimpanzee-like capabilities of Australopithecus to modern humans in only a few million years. Again, this is a very active area of research, and there are differences of opinion amongst experts. This is the nature of science at the frontier of knowledge, and this is what makes science exciting and successful. The model we are focusing on is the most widely accepted theory of human evolution. It is known as the recent single origin hypothesis, or more colloquially, the out of Africa model, and the dates and locations we've described so far might be referred to as textbook. There is broad consensus, therefore, about the when and the where, but not why. And it is to why that we now turn. There's a trend towards larger brain size over the 4 million years since the emergence of Australopithecus, but the trend is not gradual. There's a large jump around 1.8 million years ago with the emergence of Homo erectus, and another jump just under 1 million years ago with Homo heidelbergensis. The final jump occurs when Homo sapiens emerges 200,000 years ago. The time period around 1.8 million years ago also corresponds to a leap in the number of hominin species present in the Rift Valley. There were at least 5 or 6 species living side by side, suggesting that something interesting occurred around this time, which may have been responsible for, or was a contributing factor to, the observed increase in brain size, particularly in Homo erectus. The large number of deep-water lakes appearing temporarily in the Rift Valley around 1.8 million years ago indicates that at this time the climate, and in particular the level of rainfall, was varying quickly and violently. Similar climate variation occurs around 1 million years ago and 200,000 years ago, and this appears to be correlated with increase in hominin brain size. The theory is that rapidly changing climatic conditions in the Rift Valley at these specific times played an important role in driving the increases in brain size. The selection pressures that may have led to these increases are unclear. Selection for adaptability was probably an important factor, but social factors such as the ability to live in large groups and intraspecies competition as a result of the larger number of species living side by side, particularly around 1.8 million years ago, must also have played a role. Having said that, it does appear that climate variation in the Rift Valley 1.8 million, 1 million and 200,000 years ago could have been a contributing factor to the development of our intelligence. This is known as the pulse climate variability hypothesis. We can now bring all these threads together to reveal a surprising and, for me, dizzying hypothesis, which, if correct, sheds new light on the immensely contingent nature of the existence of our modern civilization, or, in simpler language, why we are bloody lucky to be here. The 3 dates, 1.8 million, 1 million and 200,000 years ago, correspond to the times when the Earth's orbit was at its most elliptical. As described earlier, the mechanism by which climate changes due to precession at these times is well understood. The pulse climate variability hypothesis asserts that the unique geology and position of the Great Rift Valley amplified these changes, and that early hominins responded by increasing their brain size. If this is correct, our brains evolved as a response to changes in the Earth's orbit, driven by the precise arrangement of the orbits of the other planets around the Sun, and precession, driven primarily by the gravitational interaction between the Moon and Earth's axial tilt, both of which date back to a collision early in the history of the solar system. And all this is plainly blind luck. Without an inconceivably unlikely set of coincidences, and the way these conspired together to change the climate in one system of valleys in wonderful Ethiopia, we wouldn't exist. If this is correct, then what a response. I held a brain for the cameras at St. Paul's Teaching Hospital in Addis. It is the most complex single object in the known universe, a most intricate example of emergent complexity, assembled over 4 billion years by natural selection, operating within the constraints placed upon it by the laws of physics and the particular biochemistry of life on Earth. The brain contains around 85 billion individual neurons, which is of the same order as the number of stars in an average galaxy. But that doesn't begin to describe its complexity. Each neuron is thought to make between 10,000 and 100,000 connections to other neurons, making the brain a computer way beyond anything our current technology can simulate. When we do manage to simulate one, I have no doubt that sentience will emerge. Consciousness is not magic. It is an emergent property consistent with the known laws of nature. But that doesn't lessen the wonder one iota. Out of this evolutionary marvel, we emerge. Thoughts, feelings, hopes, and dreams exist on Earth because of electrical activity inside a 1.5 kilogram blob of stuff, which hasn't changed much since the earliest modern humans began the long journey out of Africa. If you could travel back in time and bring a newborn baby from 200,000 years ago into the 21st century, allowing it to grow up in our modern society with a modern education, it could achieve anything a modern child could. It could even become an astronaut. Which sets up one more question. If the hardware was present 200,000 years ago, then what changed to lift us from the Great Rift Valley into space? The best thing we can do now is just to listen and hope, said Cliff Mitchellmore, broadcasting from the BBC studios 24 minutes from the expected splashdown of Apollo 13. On the 17th of April 1970, I was too young to watch the live broadcast, but I've seen the recording many times since. Grainy pictures from the deck of the USS Iwo Jima, its flight deck crammed with nervous sailors off the coast of Samoa. Patrick Moore and Geoffrey Pardo, grim-faced in the studios, and James Burke famously with fingers crossed behind his back. Apollo Control, Houston, we've just had loss of signal from Honeysuckle. Honeysuckle Creek Tracking Station in Canberra, Australia, was the last ground station to contact Apollo 13 before it entered the Earth's atmosphere on its way home. Signal loss during re-entry is routine high drama on all space missions. The ionization of the atmosphere caused by the frictional heating of the spacecraft blocks radio signals, typically resulting in radio silence for 4 minutes. On Apollo 13, 6 minutes passed in silence. The brilliance of the BBC's quartet of commentators was in the silence they allowed on the airwaves. The only sound was the static of the NASA feed, a moment of genuine tension. No need for vacuous media babble. Nobody could bring themselves to speak. We'll only know whether that heat shield was damaged by that explosion 3 days ago, when they come out of radio blackout in just over 2 minutes, said Burke. Silence. As 4 minutes passed, Houston reports, 10 seconds to end of radio blackout. Silence. Houston. We've had a report that Orion 4 aircraft has acquisition of signal. They're through, says Burke. Let's not anticipate because the parachutes may have been damaged. Chutes should be out, murmurs Burke, not broadcasting, just saying. There they are! There they are! They've made it, remarks Moore, and then applause. I make it no more than 5 seconds late, shouts Burke. No more than 5 seconds late. The safe return of Apollo 13 was arguably NASA's finest hour. 55 hours, 54 minutes, and 53 seconds into the mission, 320,000 kilometers from Earth, Lunar Module pilot Jack Swigert switched on a system of stirring fans in the hydrogen and oxygen tanks in the service module, a routine procedure. A piece of Teflon insulation inside the tank had been damaged, it was later discovered, by a series of unlikely events that happened on the ground during the preparation of the spacecraft for flight. The wire shorted, the tank exploded, and the side of the service module was blown off, critically damaging the spacecraft's power supply systems and venting the crew's oxygen supply out into space. The command module, the only part of the spacecraft capable of surviving a re-entry through the Earth's atmosphere, was now running on batteries, and with a rapidly diminishing oxygen supply that would not keep the astronauts alive long enough to return to Earth. The only option was to shut down the command module and retreat to the lunar module, effectively using it as a life raft. Lovell later spoke of how he didn't regret the mission at all. He was robbed of his moon landing, which must have been doubly frustrating given he'd already flown to the moon on the historic Apollo 8 mission. But his reaction, revealed in interviews in later life, offers great insight into the character of a test pilot. "We were given the situation," Lovell explained, "to really exercise our skills and our talents to take a situation which was almost certainly catastrophic and come home safely. That's why I thought that 13 of all the flights, including Apollo 11, that 13 exemplified a real test pilot's flight." Both Lovell and Hayes have said that the idea of not returning safely to Earth never really came up. There was nothing there that said irrefutably, "We don't have a chance." Hayes was correct, of course, because they did return safely. But they only had enough food and water to sustain 2 people for a day and a half, and had to improvise a carbon dioxide filter to provide them with enough breathable air for the return journey. Locked in the lunar module with limited supplies of food and water, and temperatures dropping towards freezing, life was far from comfortable. With the command module powered down to preserve the sparse battery supplies left after the loss of the fuel cells, the crew had to survive in a hostile environment with limited resources. Like so many outposts of human civilization throughout history, shortage of water was a primary concern. Water was critical on the lunar module for 2 reasons. As well as being needed to keep the crew hydrated and to rehydrate the food, it also cooled the electrical systems on the spacecraft. Conserving water therefore became a critical part of the plan to return to Earth. Reducing their intake to just 1/5 of a normal human water ration, each of the crew suffered severe dehydration, and together they lost 31.5 pounds in weight, nearly 50% more than any other Apollo crew. Despite the discomfort, setting a new mission trajectory and navigating their way along it remained the primary challenge. The standard way to make in-flight course corrections on Apollo was to use the command module's main engine. But the system was located close to the damaged site, and mission controllers decided that lighting it was too great a risk. Instead, the decision was made to use the LM's descent engine to send them around the far side of the Moon and back to Earth in 4.5 days. This is known as a free return trajectory, a slingshot around the Moon at the correct angle to return directly to Earth. No one knew if an engine designed for a completely different purpose would perform this function successfully. But they knew that if it failed, they would not return. 5 hours after the initial explosion, the LM engine was fired for a 35-second burn, successfully putting the crew onto a free return trajectory. This solved one problem, but raised another. Calculations of the trajectory estimated return to Earth 153 hours after launch, which would push the key reserves on the craft too low for comfort. So it was decided to speed up the spacecraft with another burn, cutting the total time of the voyage by 10 crucial hours. Such were the slim margins on Apollo 13. The main navigation system in the command module was out of action, so Lovell had to calculate the correct navigational inputs, while back at base, Mission Control worked through the same calculations as a cross-check. Lovell also got to use his sextant, which he played with on Apollo 8, to navigate by the stars for real. The calculations are preserved as handwritten notes in the Lunar Module Systems Activation Checklist. This was the checklist Lovell and Hayes would have used to fly down to the moon's surface. Now useless, Lovell used the waste paper to write down instructions to put the ship on course for Earth. 2 hours after they rounded the far side of the moon, the LM engine fired, following Lovell's handwritten checklist, increasing the speed of the spacecraft by 860 feet per second and buying them 10 precious hours. The most dramatic rescue in the history of human spaceflight stands as a testament to the brilliance of the 3 test pilots Lovell, Hayes and Swigert, and also to the brilliance of the engineers on the ground, who simply knew their stuff. NASA's Apollo engineers were young by today's standards. The average age of the team in mission control for the splashdown of Apollo 11 was 28 years old. This is one of the reasons why the United States reaped such a colossal economic reward from its investment in Apollo. The generation of scientists and engineers who worked on and were inspired by Apollo went out into the wider economy and delivered a huge investment return. A series of studies, including one by Chase Econometrics, showed that for every dollar invested in Apollo, at least $6 or $7 was returned as increased GDP growth. This should, of course, be bloody obvious. New knowledge grows GDP. But every generation of politicians seems to require re-educating to understand the difference between spending and investment. And while I'm polemicizing, let me say that the usual political argument that public support is needed for such large investments is drivel. Firstly, the investment in NASA wasn't that large, never exceeding 4.5% of the federal budget throughout the lifetime of Apollo. And secondly, it is a politician's job to lead from the front. Make the case that investment in knowledge, in pushing the boundaries of human capabilities and exploring all frontiers, both physical and intellectual, is the key to the future wealth, prosperity, and security of civilization. Aspire to be Kennedy, not a hand-wringing apologist for intellectual and technological decline. The 9 Apollo flights to the moon remain the furthest modern humans have explored beyond the Rift Valley in our 200,000-year history. Homo sapiens first left Africa in large numbers 60,000 years ago. So on geological timescales, we didn't hang around. Our ancestors followed waves of earlier hominins. Homo erectus were in Southeast Asia 1.6 million years ago, and 500,000 years later Neanderthals had colonized Europe, and Homo floresiensis were in southern Asia. The details of the migration 60,000 years ago are particularly well understood as a result of the combination of genetic, archaeological, and linguistic studies. The precision comes in part from the tracking sequences of mitochondrial DNA, which is passed down from the mother and not shuffled by sex. This makes it relatively stable and easy to track. Changes are caused by mutations alone. The most widely accepted interpretation of the data suggests that a small population of between 1,000 and 2,500 individuals left East Africa 60,000 years ago and moved north across the Red Sea and through Arabia. The group then split, moving into southern Europe 43,000 years ago and travelling through India and into Australia on roughly the same timescale. The crossing into North America via eastern Russia was probably later, around 15,000 years ago. These early groups of humans were hunter-gatherers. It's been estimated that the basic social units would have reached a maximum of around 150 individuals. This is known as Dunbar's number, after the British anthropologist Robin Dunbar, who suggests that the largest social group amongst any given population of primates is related to the size of their brains, specifically the neocortex. Dunbar's number can be observed today in the size of the average person's social network, both in the real world and online. Our hardware, the brain, has not changed appreciably since the first humans appeared in Africa 200,000 years ago. These social groups would have lived in loosely bound tribes, perhaps reaching a size of between 1,000 and 2,000 individuals, operating within an area of around 100 kilometers. Populations would stabilize, perhaps in response to social factors, but also as a result of increased mortality rates caused by parasitic diseases and diminishing per capita resource availability, before fragmenting and spreading. In this fashion, the rate of progression of our ancestors across the globe has been estimated to have been around 0.5 kilometers per year, or 15 kilometers per generation. Population density did not rise significantly beyond these levels until these proto-societies shifted from a hunter-gatherer lifestyle to agriculture around 12,000 years ago. This shift was the trigger for the development of civilization, the most important single step following the migration out of Africa in the journey from ape-man to spaceman. There are many competing theories as to the reason for the domestication of crops, but many note the correlation between the first evidence of agriculture and the beginning of the current interglacial period known as the Holocene, 12,000 years ago. In the Fertile Crescent around modern-day Jordan and Syria, people known as the Natufians were beginning to settle into larger communities, perhaps because of the relatively benign climate. The area would have been forested and rich in wild cereals, fruits and nuts rather than the austere desert of today. One theory is that a brief 1,000-year cold period known as the Younger Dryas, beginning around 10,800 BCE, triggered drier conditions in the region, forcing the Natufians to begin cultivating the previously abundant wild crops on which they had come to rely. Whatever the reason, it's generally agreed that the foundational crops of modern agriculture, including wheat, barley, peas and lentils, were all to be found in the Fertile Crescent by 9,000 BCE, and by 8,000 BCE the banks of the Nile were being cultivated. At approximately the same time, evidence of farming can be found in Asia's Indus Valley, in China, and in Mesoamerica. This suggests that there was no single environmental or developmental cause for agriculture, because it appeared independently at many sites across the world. Rather, our large brains and relatively large social groups were ready to take up the challenge when the need arose. Once agriculture was established, larger numbers of people could live together, taking advantage of the more stable food supply. The freedom from continual hunting and gathering would have introduced a new aspect to human life, free time, and it was used to great effect. Some of the earliest farmers settled in a place known as Beida in modern-day Jordan around 7,000 BCE. Living in round stone-built houses, they grew barley and wheat and kept domesticated goats, engaged in ritual and ceremony, and buried their dead. Importantly, each of these activities was carried out in specific areas of the settlements, the beginning of town planning. By the 2nd century BCE, a Semitic people known as the Nabateans lived around Beida. They employed new technologies to increase the reliability of farming, and constructed walled agricultural terraces on the hillsides around the village to collect and store water. Animal husbandry was also expanding, with the domestication of cows, pigs, donkeys, and horses. Even previously dangerous animals were coerced into living with humans. There is evidence that the Nabateans kept dogs. As the great empires of Egypt, Greece, and Rome prospered, the Nabateans remained partially nomadic, driving their camel trains across the desert along the long-established trade routes between North Africa and India, and the great cities of the Mediterranean. But then, around 150 BCE, they decided to try something different. A few kilometers south of Beida, in a narrow gorge naturally formed in the soft sandstone rock, they built the city of Petra. Today, tourists stream through a magnificent passageway lined with buildings carved out of the desert rocks and known as the Sikh. But 2,000 years ago, the great and good of Mesopotamia, Rome, and Egypt would have walked this route into this jewel of late antiquity. The grandeur of the buildings is still overwhelming. They stand not as great architecture for their time, but as simply great, with no caveat. The most famous is called Al-Khazne, which means treasure box, because of the carved urn above the entrance, which Bedouin legend has it contains the treasure of a pharaoh. Monumental architecture is a common feature in the rise of human civilization. It is a statement of power and grandeur to impress and cow outsiders, but it also serves an internal purpose, cementing the position of the rulers in the hierarchy and therefore providing the stability and security on which civilization rests. Over time, a virtuous circle emerges. The buildings help the civilization prosper, and the more prosperous the civilization, the more impressive the buildings become. Petra's wealth was derived from its location. Built within a natural gorge, the area is prone to flash floods, which provided precious water in a landscape that was arid by the time the Nabateans began to build. The city also sits at the fulcrum of the ancient nomadic trade routes along which wood, spices, incense, and dyes were transported from Africa and India and into the great Mediterranean civilization beyond. The appetite of the Greeks and Romans for exotic goods was insatiable. Black pepper alone fetched 40 times its own weight in gold in a Roman market. Petra, because of its strategic location, controlled all that trade and taxed it. Today, 1,500 years after the city was abandoned, it is still a magnificent sight, an overused but entirely accurate statement. Talk to an archaeologist, however, and you quickly realize how much more impressive it would have been in its heyday. The hillsides running down the valley from the carved tombs are scattered with rocks, but closer inspection reveals them to be bricks, the remains of houses, temples, and palaces. Everything from Al-Khazne to the houses would have been covered in white plaster and painted in bright colours which would have appeared resplendent against the monochrome desert sands. To build on this scale required a huge labour force. Petra was home to at least 30,000 people living in a few square kilometres of desert. Such a population density required technological innovation on a metropolitan scale, and the Nabateans, perhaps more than any other civilization in antiquity, were masters of fluid engineering. Virtually every drop of rainwater that fell on the surrounding hillsides was captured in grooves and stored in giant reservoirs and cisterns. They were better at plumbing than the Romans, who employed the Petran engineers in Rome. Petra had the world's first pressurized water system, which could deliver 12 million gallons of water a day into the city. Outside the city, the irrigation system continued out into the surrounding fields, lining the hillsides in still visible terraces. The Nabateans didn't simply build a city, they terraformed a landscape. I stood and imagined the ancient valley views with some awe. The mountain slopes would have been green with maize, barley, pulses, and vineyards. A desert turned green and feeding this grandest of desert civilizations for 6 centuries. Whenever I see the ruins of Petra, Rome, Athens, or Cairo, I wonder what Earth would be like today if the great civilizations of antiquity had not fallen. I blame the philosophers for not discovering the scientific method earlier and inventing the electric motor. How hard can it be? Agriculture, then, was fundamentally important to the rise of civilization because it enabled large numbers of people to live in one place and gave them access to resources and time which would have been unavailable to hunter-gatherers. With resources and time comes the division of labour, freeing up a small but important subset of individuals to engage in pursuits other than those necessary for immediate survival. Farmers, stonemasons, priests, soldiers, administrators, and artisans emerge, together with a ruling class who begin to direct the construction of monumental architecture, partly for their own selfish ends, and cities like Petra become possible. Petra was a relative latecomer in the emergence of the cities and civilizations of antiquity. The first great ancient civilization, the Old Kingdom of Egypt, arose around 2600 BCE along the fertile and farmed banks of the Nile, and precisely the same pattern of agriculture, followed by social stratification, ritual, and monumental architecture, can be seen. Present also in the Old Kingdom, and possibly developed there, was the one final vitally important innovation we will soon discuss: the written word. It all seems so simple when written down on a piece of paper. The BBC prepares something known as a call sheet, which tells a film crew everything they need to know about a trip. Call sheets are very neat. All the timings work beautifully, carefully documenting flights, ground transfers to locations, and filming and rest periods, all of course in accordance with health and safety regulations and all that. Things never quite work out the way they're envisaged back in the office, of course. But filming the return of the Expedition 38 crew from the International Space Station to the Kazakh steppe in March 2014 was the wildest adventure I've experienced. The call sheet said that we would fly into Astana on the 8th of March, arriving at 1 a.m. on the 9th into our hotel. After a leisurely breakfast at 9 a.m., we drive to a city called Karaganda, which has a spectacular statue of Yuri Gagarin in the town square. There we'd meet up with our drivers, who, embedded with Roscosmos, the Russian space agency, would drive us out to the landing site the following morning, arriving in time for a hot meal and a good rest on the steppe, ready to film the landing on the morning of the 11th, after, of course, a hot breakfast. We'd then drive back to the airport, hop on a flight, and be home in time for lunch on the 12th. A doddle. Bollocks. The steppe of central Kazakhstan in March is a featureless frozen wilderness covering around 800,000 square kilometres of the country's interior. There are no towns and few roads, just tufts of stunted brown grass and snow fading into an ice-grey leaden sky. In March 2014, temperatures were unseasonably cold, falling below -20 degrees C at night, and it was snowing. Our team had standard 4x4 vehicles, which got stuck in the snow by mid-afternoon the day before the landing, even though we'd set off 3 hours earlier than the 6 a.m. officially sanctioned health and safety call time because of the weather. This was problematic because our 8-man spaceman film was constructed carefully around this moment, the return of 3 human beings from space. Over vodka, cold meat and bread, we discussed our options. We'd been helped along the snowy roads by a Russian team from the Siberian city of Tobolsk in 2 spectacular 6-wheel drive vehicles hand-built by a company called Petrovich. Tobolsk is best known for being the place dissidents were sent during the Soviet era. Tsar Nicholas II and his family enjoyed the Tobolskian hospitality for a year before being transported to Ekaterinburg to be shot. Mendeleev, the inventor of the periodic table, was born there, but so was Rasputin. It's a tough place, and they know how to build tough vehicles. Our guide from Roscosmos managed to radio the Petrovich team, and they agreed that if we could catch them up in the frozen wilderness, they could take 2 of us out to the landing site. The cameraman and I jumped aboard a pair of snowmobiles and headed out into the rapidly dimming late afternoon twilight in search of the men from Siberia. It was a difficult decision to jump on the snowmobiles. We didn't have a satellite phone because they are illegal in Kazakhstan, and nobody spoke English, so we couldn't quite assess the level of difficulty associated with finding these 2 Siberian needles in a Kazakh steppe. And we didn't know who the Siberians actually were. It seemed that they were freelancers, hired to take photographs and broadcast live television pictures back from the landing site for the Russian space agency. We also had to decide whether we could make the film with only 2 people. Much as I spend a lot of time dreaming about jettisoning directors, producers and executives, there is a reason why we usually take a crew of 6. Sound is particularly important. You don't really miss the sound man until he's not there. Our sound man on the series is called Andy, but we always called him Sound Man. There are too many other things to remember. As it turned out, the Petrovich crew were a hospitable and professional bunch, although their willingness to spend many days out in the wilderness waiting for the Soyuz, they'd driven down from Siberia and were in no hurry to get home, played on our minds. Approaching midnight on the night before the landing, we received a message from Roscosmos that the landing might be postponed due to the poor weather, and the decision was made to camp out on the steppe and wait. In the distance we could make out a small group of farm buildings through the snow, and we headed towards them. In broken English, one of the crew told us that it is a Kazakh tradition to welcome travellers into your home, at any time of the day or night, and offer them food. And so we found ourselves inside a farmhouse that appeared to have heated walls and resembled the inside of an oven, eating a feast of jam, bread, assorted sweets and horse, all washed down with vodka, which the Petrovich crew carried in large crates alongside their satellite broadcasting hardware. It was unforgettable. At 4 a.m., soaked in vodka, the call came through. Commander Oleg Kotov, Sergei Ryazansky and Mike Hopkins had climbed aboard the Soyuz and were preparing to depart the International Space Station. I was elated, because I genuinely thought the landing would be called off, and I had no idea what that would have meant other than waiting for the storms to clear on the steppe. At 6:02 Kazakh time, the Soyuz TMA-10M, the 199th Soyuz to fly since 1967, undocked from the ISS. This is the point of no return, except in an emergency. Just 2 hours and 28 minutes later, it fired its engine for a pre-programmed burn of 4 minutes and 44 seconds. This reduced the spacecraft's velocity by 128 meters per second relative to the station, which in its orbit that day was travelling at 7,358 meters per second. That number is not arbitrary. It is given by a simple equation which can be derived easily from Newton's law of gravitation and his second law of motion, F equals ma. We leave it as an exercise for the listener to show that these two laws of nature can be rearranged to show that the velocity v of any object in a circular orbit a distance r from the centre of the Earth, mass me, is given by v equals the square root of gme over r. To derive this result, you need to know that the force required to maintain an object of mass m in a circular orbit is mv squared over r. The space station orbits at an altitude of between 330 and 445 kilometers. Let's choose the middle ground of 387 kilometers. This is a back-of-the-envelope calculation. Estimate is the name of the game, as my old physics teacher used to say at school. The radius of the Earth is 6,378 kilometers, and the mass of the Earth is 5.97219 times 10 to the 24 kilograms. Newton's gravitational constant is 6.67384 times 10 to the minus 11 meters cubed per kilogram per second squared. Do the calculation yourself. Maths is good for you. With these numbers, v is approximately 7,675 meters per second, which is close enough. The difference is due to the precise altitude of the ISS that day. I love doing little calculations like this. They reveal the immense power of mathematical physics. This really is the orbital velocity of the International Space Station, and it is forced to be so by laws of nature first published by Isaac Newton in 1687. If you've never done a calculation like this before, you should feel elated. The biologist Edward O. Wilson called this feeling the Ionian enchantment, a poetic term he introduced to describe the realization, credited to Thales of Miletus in 600 BCE, that the natural world is orderly and simple, and can be described with great economy by a small set of laws. It is nothing short of wonderful that we can calculate the orbital velocity of the International Space Station together, and this points us neatly towards the story of the last great innovation in the ascent from ape-man to spaceman. I began my degree at the University of Manchester in 1992, which is when I started doing physics full-time. I gained my PhD in 1998 and spent the next 11 years working as a particle physicist at the DZ laboratory in Hamburg, Fermilab in Chicago, and CERN in Geneva. In 2009, I began filming Wonders of the Solar System, which slowed down my research a bit. But I've been at it now for 22 years, which is almost half my life. In that time, I've learnt a lot about how to be a scientist, how to think about scientific problems, how to make measurements of nature, particularly the behavior of subatomic particles, and how to interpret those measurements to generate new knowledge and make new discoveries. But given all that, there's no way I would be able to calculate the orbital velocity of the International Space Station from scratch. Given Newton's laws, it's trivial. Without them, it would be virtually impossible. Newton's laws are far from obvious. They took Newton a scientific lifetime to produce, and he was a genius, one of the greatest scientific minds of all time. And even he didn't start from scratch. He relied heavily on the previous works of Galileo, Euclid, and 100 other philosophers, geometers, and mathematicians whose names have been forgotten, but whose works remain as cornerstones of our scientific culture. The reason we could run through that simple calculation together is that the thoughts and discoveries of these generations of philosophers, scientists, and mathematicians were not lost. They were preserved forever in the written word. Writing appears to have arisen independently in several different cultures, just as with the development of agriculture. And just as agriculture triggered the birth of civilization 12,000 years ago, so the emergence of writing supported a rapid increase in the complexity of civilization. The earliest known system of writing is generally accepted to be cuneiform, the Sumerian system that emerged around 5,000 years ago in the cities of Mesopotamia, although it's possible that Egyptian hieroglyphs may predate it. Literally meaning wedge-shaped, cuneiform comprises 1,000 or more symbols created using a stylus made from reed that was pressed into a soft clay tablet. Following cuneiform and hieroglyphs, other forms of script emerged in Greece, China, India, and later Central America. Writing seems not to have arisen out of a deep human need to share and record intimate thoughts and lay down knowledge for future generations. That would be far too romantic. Rather, it appears to have served a more practical purpose, revealed in a set of around 150 Nabatean scrolls discovered by archaeologists in 1993. The scrolls date from around 550 CE, in the final period before Petra was abandoned. One of the most intact documents relates to a court case between two priests. It is alleged that one of the priests decided to run away from their shared house, taking a key to one of the upstairs rooms, 2 wooden beams that presumably held the roof up, 6 birds, and a table. This is probably how writing began. The invention upon which modern human history rests arose, disappointingly, for admin purposes. This is seen not only in the relatively late Nabatean scrolls, but in many of the early texts. Cuneiform developed because of a need to keep track of trade and accounts in the increasingly complex economy of Mesopotamia. Egyptian hieroglyphs may be an exception, as there is a strong ritual component, but there's also evidence of their early use in commerce, administration, trade, and law, the foundations of a modern society. Information about the natural world was also recorded. In hieroglyphs we see the cycle of the seasons chronicled, as well as important environmental events. There are also some beautiful early examples of the use of writing to express deeper human desires and feelings that resonate strongly today, and show yet again that our ancestors had inner lives not too distant from our own. But the oldest surviving papyrus documents from the Old Kingdom are marvellously prosaic. From Dynasty 5 in the reign of Pharaoh Djedkare-Isesi between 2437 and 2393 BCE can be found an early version of the parrot sketch. As Re, Hathor, and all the gods desire that King Isesi should live forever and ever, I am lodging a complaint through the commissioners concerning a case of collecting a transport fare. And so the letters continue. Whilst the tombs are covered in the names of pharaohs and stories of the gods, the people of Egypt were using writing as we do today, and I find it wonderful, reassuring, and moving in a funny sort of way to hear ancient voices complaining down the years. Perhaps we humans really will never change. From Dynasty 20, a millennium later, during the reign of Ramesses III and IV between 1182 and 1145 BCE, the complaints continue. The scribe Amenacht, your husband, took a coffin from me, saying, I shall give the calf in exchange for it, but he hasn't given it until this day. I mentioned this to Pachet, who replied, Give me a bed in addition to it, and I will bring you the calf when it is mature. And I gave him the bed. Neither the coffin nor the bed is yet here to this day. If you are going to give the ox, send it on, but if there is no ox, return the bed and the coffin. Alongside the letters, the ritual, the complaints, the admin, and the legal documents, there was also a sophisticated literary and storytelling tradition in ancient Egypt, and a powerful appreciation of the value of the written word. 3,000 years ago on the banks of the Nile, during the reign of Queen Tuusret, somebody wrote a eulogy for the writers. These sage scribes, their names endure for eternity. Although they are gone, although they have completed their lifetimes and all their people are forgotten, they did not make themselves pyramids of bronze with stelae of iron. They made heirs for themselves, as the writings and teachings that they begat. Departing life has made their names forgotten. Writings alone make them remembered. Taken from the Tale of Sinuhe and Other Egyptian Poems, 1940 to 1640 BC. Writing was the final pivotal moment in our ascent from early agrarian civilizations to the International Space Station, because it frees the acquisition of knowledge from the limits of human memory. The hardware restrictions set down in the Rift Valley 200,000 years ago no longer matter. Writing allows a practically unlimited amount of information to be passed from generation to generation and to be shared across the world. Knowledge is no longer lost, but is always added to. It becomes widespread, accessible, and permanent. A little boy from Oldham, Lancashire, can inhabit the mind of Newton, assimilate his lifetime's work, and derive new knowledge from it. Writing created a cultural ratchet, an exponentiation of the known, that allowed humanity to innovate and invent way beyond the constraints of a single human brain. We now work together as a single mind spread across the planet, and with a memory as long as history. It is this collective effort, enabled by the written word, that carried us, the human race, paragon of animals, from the great Rift Valley to the stars. I deliberately borrow from Shakespeare. The most precious objects on earth are not gems or jewels, but ink marks on paper. No single human brain could conceive of Hamlet, Principia Mathematica, or Codex Leicester. They were created by and belong to the entire human race, and the library of wonders continues to grow. Johannes Kepler is rightly best known for his laws of planetary motion that paved the way for Newton to write Principia. Hidden within his illustrious CV, however, is a publication that had a rather more whimsical, earthbound ambition. 2 years after publishing the first part of Astronomia Nova in 1609, Kepler published a short 24-page paper entitled De Nive Sexangula, on the six-cornered snowflake. It is a beautiful example of a curious scientific mind at work. In the dark December of 1610, Kepler was walking across the Charles Bridge in Prague when a snowflake fell on the lapel of his coat. In the freezing night he stopped and wondered why this ephemeral sliver of ice possessed a six-sided structure, in common with all other snowflakes, notwithstanding their seemingly infinite variation. Others had noticed this symmetry before, but Kepler realized that the symmetry of a snowflake must be a reflection of the deeper natural processes that underlie its formation. Since it always happens when it begins to snow, that the first particles of snow adopt the shape of small six-cornered stars, there must be a particular cause, wrote Kepler. For if it happened by chance, why would they always fall with 6 corners and not with 5 or 7? Kepler hypothesized that this symmetry must be due to the nature of the fundamental building blocks of snowflakes. This stacking of frozen globules, as he referred to it, must be the most efficient way of building a snowflake from the smallest natural unit of a liquid like water. To my mind, this is a leap of genius, and a tremendously modern way of thinking about physics. The study of symmetry in nature lies at the very heart of the Standard Model, and abstract symmetries known as gauge symmetries are now known to be the origin of the forces of nature. This is why the force-carrying particles in the Standard Model are known as gauge bosons. Kepler was searching for the atomic structure of snow before we knew atoms existed, motivated by the observation of a symmetry in nature, the six-sided shape of all snowflakes. The inspiration for this idea, which is way ahead of its time, came from a peculiar source. In the years leading up to the publication of De Nive Sexangula, Kepler had been in communication with Thomas Harriot, an English mathematician and explorer. Amongst multiple claims to fame, Harriot was the navigator on one of Sir Walter Raleigh's voyages to the New World, and had been asked to solve a seemingly simple mathematical problem. Raleigh wanted to know how best to stack cannonballs to make the most efficient use of the limited space on the ship's deck. Harriot was driven to explore the mathematical principles of sphere packing, which in turn led him to develop an embryonic model of atomic theory, and inspire Kepler's consideration of the structure of snowflakes. Kepler imagined replacing cannonballs with globules of ice, and supposed that the most efficient arrangement creating the greatest density of globules was the six-sided hexagonal form he observed in the snowflake on his shoulder. Kepler also observed hexagonal structures across the natural world, from beehives to pomegranates and snowflakes, and presumed that there must be some deeper reason for its ubiquity. Hexagonal packing, as Kepler referred to it, must be the tightest possible, so that in no other arrangement could more pellets be stuffed into the same container. This became known as the Kepler conjecture. It took almost 400 years to prove Kepler's conjecture, and this required the help of a 1990s supercomputer. Despite the time lag, Kepler's work had a more immediate impact, inspiring the beginnings of modern crystallography that led eventually to the discovery of the structure of DNA. What a lovely example of serendipity coupled with curiosity and a sprinkling of genius. From cannonballs to snowflakes to the code of life. As for Kepler's original thought on that frozen bridge, he never found the connection between the underlying structure of his ice globules and the hexagonal symmetry of snowflakes. Even though he realized that the regular patterns must reveal something about the shape of the building blocks of snowflakes and the details of the packing, he couldn't explain the ornate complexity or the flatness of the structure. Instead, he acknowledged his failure with the good grace of a true scientist. "I have knocked on the doors of chemistry," he writes at the end of his paper, "and seeing how much remains to be said on this subject before we know the cause, I would rather hear what you think, my most ingenious man, than wear myself out with further discussion." 3.5 centuries later, Japanese physicist Yukichiro Nakayara made the first artificial snowflakes in a laboratory. Writing in 1954, he describes a process that begins not with the snowflake itself, but with smaller substructures called snow crystals, which are in turn built up from collections of ice crystals, the globules Kepler was searching for. The hexagonal packing that Kepler suspected to be the origin of the snowflake symmetry begins with the formation of these ice crystals, when water molecules link together in a hexagonal structure via hydrogen bonds. Hydrogen bonding occurs because of the structure of the water molecules themselves, with a greedy oxygen atom hungry for electrons grabbing them off 2 hydrogen atoms, forming covalent bonds that lock the H2O molecules together, leaving a residual positive electrical charge in the vicinity of the 2 protons and a negative charge in the vicinity of the oxygen. This slight separation of charge in the water molecules allows them to bind together into larger structures through the mutual attraction and repulsion of the electrical charges, just as an electron is bound into its position around an atomic nucleus. The entire configuration, including the structure of the oxygen nucleus and the single protons that comprise the hydrogen nuclei, can be predicted in principle by the standard model of particle physics. Yet the details of any particular snowflake are beyond computation, because the seemingly infinite variety reflects the precise history of the snowflake itself. Once ice crystals form as agglomerations of water molecules held together by hydrogen bonds, they cluster around dust particles in the air, building on their underlying hexagonal symmetry to form larger snow crystals. As the crystals begin the long journey down to Earth, they join in ever larger, more complex combinations, shaped by endless variations of air temperature, wind patterns, and humidity, into myriad unique forms. The symmetry is all that remains of the simplicity, and it takes a careful and patient eye to see the endless variation for what it is, a reflection of the complex history of the snowflake, convoluted with the underlying simplicity of the laws of nature. The most vivid example of emergent complexity, and the closest to our hearts, is life. The origin of life on Earth has a sense of inevitability about it, because its basic processes are chemical reactions that will proceed given the right conditions. Those conditions were present in the oceans of Earth 3.8 billion years ago, possibly earlier, and they led to the emergence of single-celled organisms. The fateful encounter which produced the eukaryotic cell around 2 billion years ago looks rather more like blind chance, but it happened here and laid the foundations for the Cambrian explosion 530 million years ago. There is a bit of hand-waving going on here, though. and to make a more persuasive case that all the complexity of Darwin's endless forms most beautiful can at least in principle emerge from simple underlying laws, one more example is in order. Perhaps the most beautiful manifestation of the artful complexity of nature can be found in the spots, stripes, and patterns on the coats and skin of living things. Emergent pattern writ large across venomous striped surgeonfish, emperor angelfish, zebra swallow-tailed butterflies, and the big cats of Africa and Asia. Everyone agrees that these patterns evolved as a result of natural selection of one form or another, and the raw material for the variation was provided by random mutations in the genetic code. But a very challenging scientific question of fundamental importance in modern biology is precisely how patterns such as these appear. How the leopard got its spots. Zebra moved away to some little thorn bushes where the sunlight fell all stripy, and the giraffe moved off to some tallish trees where the shadows fell all blotchy. "Now watch," said the zebra and the giraffe. "This is the way it's done. 1, 2, 3, and where's your breakfast?" All they could see were stripy shadows and blotched shadows in the forest, but never a sign of zebra and giraffe. "That's a trick worth learning. Take a lesson from it, leopard." Then the Ethiopian put his 5 fingers close together and pressed them all over the leopard, and wherever the 5 fingers touched, they left 5 black marks all close together. Rudyard Kipling's Just So story, How the Leopard Got His Spots, tells the story of an Ethiopian man and a leopard. They went hunting together, but one day the man noticed that the leopard wasn't very successful. The reason, he deduced, was that the leopard had a plain, sandy coat, whereas all the other animals had camouflage. "That's a trick worth learning, leopard," he said, taking his fingers and thumb and pressing them into the leopard's coat to give it the distinctive 5-pointed pattern. If you don't believe in evolution by natural selection, this is the most plausible theory open to you. If you do, then what remains is to identify the mechanism by which the pattern is formed. The answer might appear to be solely a matter of genetics, but genes are not the whole story. It would take a terrific amount of information to instruct every single cell to colour itself according to its position on the leopard's skin, and this is indeed not what is done. Nature is frugal, and deploys a much more efficient mechanism for producing camouflage patterns. I get to say yet again that this is an active area of research, and therefore exciting. The reason for the attention is that camouflage patterns on the skin self-organize during the development of the embryo, and embryonic development is of course fundamental to an understanding of biology. In the case of the leopard, it is thought, though not proven, that the camouflage is an example of a Turing pattern, named after the great Bletchley Park codebreaker and mathematician Alan Turing. In 1952, Turing became interested in morphogenesis, the process by which an animal develops its shape and patterning. He was particularly interested in the mathematics behind regularly repeating patterns in nature, such as the Fibonacci numbers and golden ratio in the leaf arrangements of plants and the scales of pineapples, and the appearance of camouflage patterns such as the tiger's stripes and the leopard's spots. Turing's influential and groundbreaking paper, The Chemical Basis of Morphogenesis, published in March 1952, begins with a simple statement. It is suggested that a system of chemical substances called morphogens, reacting together and diffusing through a tissue, is adequate to account for the main phenomena of morphogenesis. These systems are known as reaction-diffusion systems, and they can produce patterns from a featureless initial mixture if the 2 reactants diffuse at different speeds. Imagine a dry field full of grasshoppers. They are strange grasshoppers because when they get warm, they sweat, generating a large amount of moisture. Now imagine that the field is set alight in several different places. The flames will spread at some fixed speed, and if there were no grasshoppers, the whole field would be charred. As the flames approach the grasshoppers, however, they will start to sweat, dampening the grass behind them and inhibiting the flames as they hop away ahead of the approaching flames. Depending on the different parameters, including the different speeds of the flames and the grasshoppers and the amount of sweat necessary to quell the advancing flames, a Turing pattern can be formed, with areas of charred grass and green areas where the inhibiting grasshoppers prevented the fire from taking hold. It is thought that the leopard gets its spots in this way during embryonic development. An activator chemical, fire, spreads through the skin and stimulates the production of the dark pigmented spots, charred grass, but is inhibited by another chemical, sweating grasshoppers, spreading with a higher diffusion rate. The precise pattern produced depends on the constants of nature of the system, such as the speeds at which the chemicals diffuse, and on what a mathematician would call the boundary conditions, the size and geometry of the grassy field in our analogy. In embryonic development, it is the size and shape of the embryo when the reaction diffusion begins that determines the type of pattern produced. A long and thin domain produces stripes. A domain that is too small or too large produces uniform color. In between can be found the distinctive coat patterns of cows, giraffe, cheetah, and of course the leopard. Computer simulations of Turing patterns have been remarkably successful, not only in describing the generic features, particularly of mammalian coats, but also of some of the interesting details seen in nature. For example, the mathematical models predict that it is possible for spotted animals to have striped tails, as cheetahs do, but not for striped animals to have spotted tails, and indeed no such examples exist. Kepler's snowflakes and the leopard's spots are two picturesque examples of emergent complexity, the appearance of intricate, ordered patterns from the action of simple underlying laws. Nature contains systems far more complex than these, of course, you being a case in point. But to return to the question at the beginning of our solipsistic meander, the reason that you exist, given the laws of nature, is that you are allowed to. Just as all snowflakes and all leopards' coats are unique in detail because of their individual formation histories, so you are unique because no two human beings share a common history. But we wouldn't read any deep meaning into the existence of one particular snowflake in a snowstorm, and the same is true for you. Our focus should therefore shift from trying to explain the appearance of humans or our planet or even our galaxy to a rather deeper question: the origin of the whole framework, of space-time and the laws that govern it, and the allowed structures within it. What properties of the laws themselves are essential for galaxies, planets, and human beings to exist? After all, as we've noted, the laws might be mathematically elegant and economical, but they do contain a whole host of seemingly randomly chosen numbers discovered by experimental observation and with no known rhyme or reason to them. The constants of nature, such as the strength of the forces, the masses of the particles, and the amount of dark energy in the universe. How dependent is our existence on these fundamental numbers? Our universe appears to be made for us. We live on a perfect planet, orbiting around a perfect star. This is, of course, content-free whimsy. The argument is backwards. We have to be a perfect fit for the planet because we evolved on it. But there are interesting questions when we look deeper into the laws of nature and ask what properties they must have to support a life in the universe. Take the existence of stars, for example. Stars like the Sun burn hydrogen into helium in their cores. This process involves all four forces of nature working together. Gravity kicks it all off by causing clouds of dust and gas to collapse. As the clouds collapse, they get denser and hotter, until the conditions are just right for nuclear fusion to occur. Fusion starts by turning protons into neutrons through the action of the weak nuclear force. The strong nuclear force binds the protons and neutrons together into a helium nucleus, which in itself exists on account of the delicate balance between the strong nuclear force holding it together and the electromagnetic force trying to blow it apart because of electrically charged protons. When stars run out of hydrogen fuel, They perform another series of equally precarious nuclear reactions to build carbon, oxygen, and the other heavy elements essential for the existence of life. There are many examples of apparent fine-tuning in nature. If protons were 0.2% more massive, then they would be unstable and decay into neutrons. That would certainly put an end to life in the universe because there would be no atoms. The proton mass is ultimately set by the details of the strong and electromagnetic forces and by the masses of the constituent quarks, which are set by the Yukawa couplings to the Higgs field in the Standard Model. There really isn't much freedom at all. The mother of all fine-tunes, however, is the value of our old friend dark energy, the thing that is causing our universe to gently accelerate in its expansion. Although dark energy contributes 68% of the energy density of the universe, the amount of dark energy in a given volume of space is actually small, very small, 10 to the minus 27 kilograms per cubic meter to be precise. The point is that every cubic meter of our universe has this amount of dark energy in it, and that adds up. Explaining why dark energy has this small but non-zero value is one of the great problems in cosmology, not least because if a particle physicist sits down with a quantum field theory and decides to calculate how big it should be, it turns out that it would be more naturally of the order of 10 to the 97 kilograms per cubic meter. That's a lot bigger than 10 to the minus 27 kilograms per cubic meter. Over a million times bigger, in fact. That's embarrassing for the particle physicists, of course, but from the perspective of fine-tuning, it's even worse. If the value of dark energy were only 50 times larger than it is in our universe, rather than somewhere else in this immensely large theoretical range, then it would have become dominant in the universe around 1 billion years after the Big Bang, during the time that the first galaxies were forming. Because dark energy acts to accelerate the universe's expansion and dilute matter and dark matter, gravity would have lost the battle in such a universe, and no galaxies or stars or planets or life would exist. What could possibly account for this incredible piece of luck? It can't really be luck. The odds are too long by a Geoffrey Boycott innings. One possibility is that there is some as yet unknown physical law or symmetry that guarantees that the amount of dark energy will be very close to, but not quite, zero. This is certainly possible, and there are physicists who believe that this may be the case. The other possibility, which was raised by one of the fathers of the Standard Model, Steven Weinberg, is that the value of dark energy is anthropically selected. Anthropic arguments appear at one level to be a statement of the obvious. The properties of the universe must be such that human beings can exist, because human beings do exist. This is, of course, true, but it is fairly devoid of content from a physical perspective, unless there is some way in which all possible values of dark energy, and indeed all the other constants of nature, are realized somewhere. If, for example, there exists a vast, possibly infinite swathe of different domains in the universe, or indeed an infinity of other universes, each with a different amount of dark energy selected by some mechanism from the span of allowed values, then we would indeed have a valid anthropic explanation for our special human universe. It must exist because they all do, and of course we appear in the one that permits our existence. But surely it makes no sense to take refuge in a vast infinity of universes to explain our existence. Absolutely correct. If that's why the idea is introduced, it's no better than a God of the Gaps explanation. If, however, there was some other reason, based on observations and theoretical understanding, that suggested an infinity of universes, then such an anthropic explanation for our perfect human universe would be admissible. Remarkably, and that remarkably overused word is appropriate for once, this outlandish suggestion is a widely held view amongst many cosmologists. If we look at our universe on the largest distance scales, by which I mean at distance scales far larger than the size of single galaxies, it has a number of properties that any theory of its origin has to explain. The most precise picture of the young universe we have is the photograph of the cosmic microwave background radiation, CMB, taken by the Planck satellite. This is the afterglow of the Big Bang, a photograph of the universe as it was 380,000 years after the initial hot dense phase, when the expansion had cooled things down sufficiently for atoms to form. The most obvious feature of the CMB is that it's extremely uniform, glowing at a temperature of 2.72548 degrees above absolute zero, with small fluctuations at the level of 1 part in 100,000. Those very tiny temperature differences are represented by the colors in the photograph. This uniformity is extremely difficult to explain in the standard Big Bang model for a simple reason. Our observable universe today is 90 billion light-years across. This means that if we look out to the CMB from opposite sides of the Earth, we are looking at two glowing parts of the ancient sky that are now separated by 90 billion light-years. The universe, however, is only 13.8 billion years old, which means that light, the fastest thing there is, has only had time to travel 13.8 billion light-years. Two opposite parts of the CMB could therefore never have been in contact with each other in the standard Big Bang model. And there is absolutely no reason why they should be almost precisely the same temperature. I've emphasized almost in the previous sentence because, as we noted, there are very slight variations in the CMB at the level of 1 part in 100,000, and these are very important. The universe was never completely smooth and uniform everywhere, and these variations in density are encoded into the CMB as differences in temperature. The regions of slightly greater density ultimately seeded the formation of the galaxies, and so without them we wouldn't exist. What caused these small variations in the otherwise ultra-smooth early universe? Another fundamental property of the universe that is difficult to explain is its curvature, or lack of it, which can also be measured from the CMB. Space appears to be absolutely flat, a veritable ice rink. In the standard Big Bang theory, the universe doesn't have to be flat. In fact, it requires a great deal of fine-tuning to keep it flat over 13.8 billion years of cosmic evolution. Instead, the radius of curvature is measured to be much greater than the radius of the observable universe, more than 60 orders of magnitude larger. That's a big problem. In the early 1980s, the need to explain these and other properties of the observable universe led a group of Russian and American physicists to propose a radical idea. The modern version, the best-known proponents of which are Alan Guth, Andrei Linde, and Alexei Starobinsky, is known as the theory of inflation. We'll describe a particular version of inflation below, driven by something called a scalar field, which was first described by Andrei Linde. Space-time existed before the Big Bang, and for at least some of that time was described by Einstein's theory of general relativity and a quantum field theory like the Standard Model. The central idea in quantum theory is that anything that can happen does happen. Everything that is not explicitly ruled out by the laws of nature will happen given enough time. One of the types of things permitted to exist in quantum field theory are scalar fields. Scalar fields have the property that they can cause space to expand exponentially fast. Given general relativity and quantum field theory, therefore, it must be the case that scalar fields will fluctuate into existence in such a way that an exponential expansion of spacetime is triggered. In this exponential phase, spacetime expands faster than the speed of light. This might sound problematic if you know some relativity, but it isn't. The universal speed limit exists for particles moving through spacetime, but does not apply for the expansion of spacetime itself. In a tiny fraction of a second, around 10 to the minus 35 seconds, in fact, an exponential expansion of this type can inflate a piece of spacetime as tiny as the Planck length to a quite mind-boggling size, trillions of times larger than the observable universe. Any pre-existing curvature is completely washed out, leading to a flat observable universe. It's like looking at a square centimetre-sized piece of the surface of a balloon of a light-year in radius. You won't see any curvature, no matter how hard you try. Likewise, any variations in density will be washed out, leading to the smooth and uniform appearance of the CMB. Perhaps the greatest triumph of inflationary models such as these, however, is that they don't predict a completely uniform, homogeneous and isotropic universe. Quantum theory doesn't allow for absolute uniformity. Empty space is never empty, but a fizzing, shifting soup of all possible quantum fields. Like the surface of a stormy ocean, waves in the fields are constantly rising and falling, and the exponential expansion can freeze these undulations into the universe. Remarkably, when calculations using the known laws of quantum theory are carried out, the sort of density fluctuations that result from such a mechanism are precisely of the form seen in the CMB. These quantum fluctuations are the seeds of the galaxies, and therefore the seeds of our existence, frozen into the oldest light in the cosmos, and photographed by a satellite built by the people of Earth 13.8 billion years later. Inflation in this guise explains the observable properties of our universe, and in particular all the details of the CMB, which has been measured to high accuracy. This is why it is currently widely accepted as an essential ingredient by many cosmologists. As if this wasn't enough to get excited about, however, there is much more. One obvious question that arises is this: if inflation gets going, how does it stop? The answer is that inflation stops completely naturally, but with a fascinating twist that drives right to the heart of our "why are we here" question. The scalar field driving inflation fluctuates up and down in accord with the laws of quantum theory, just like the waves on the surface of an ocean. If the energy stored in the field is high enough, inflation begins. One might expect that such a rapid expansion would dilute the energy extremely rapidly, causing inflation to stop. But scalar fields have the interesting property that their energy density can stay relatively constant as space expands. You can think of the expanding space as doing work on the field, pumping energy into it and keeping its level high. And in turn, the high level of the field's energy continues to drive the expansion. This might sound like the ultimate free lunch, and in a sense it is, almost, although gradually the energy will become diluted and decay away. The time this takes depends on the size of the initial fluctuation in the field and the details of the field itself, but in general, the higher the initial energy, the longer the field takes to fall in value as the expansion continues. An analogy often used to picture this scenario is to imagine a ball rolling down the side of a valley. The height of the ball up the valley side represents the energy density of the scalar field. When the ball is high up, the energy in the field is high, driving the inflationary expansion. As the ball rolls slowly down the valley, the energy reduces and inflation turns off. At the valley floor, the ball oscillates back and forth until it comes to rest. The scalar field likewise oscillates, and in doing so, dumps its energy into the universe in the form of particles. In so doing, it creates a hot, dense soup, which we identify as the Big Bang. In other words, inflation ends naturally, and the standard Big Bang follows. The decay of the scalar field that drove inflation is the cause of the Big Bang. Let us step back a moment and recap with broad brushstrokes, because we seem to be wandering onto Leibniz's territory, and that's an astonishing place for physics to have arrived at. Our claim is that there exists a quantum field that causes the universe to expand exponentially fast for some period of time, and in doing so, produces all the features of the universe we observe today, including the existence of galaxies and the matter out of which they are made. This is a triumph, and is now part of cosmology textbooks. Before the Big Bang, there was inflation. Fine, our philosopher friends would say, but what happened before inflation? Here we must leave the textbooks and become a little more speculative, but not too speculative. We're still going to be working within the domain of mainstream physics. There is an extension of what we might term standard inflationary theory. It's known as eternal inflation. Put simply, there seems to be no reason why inflation should stop everywhere at the same time. There should always be regions of the universe where the scalar field fluctuates to such high values that the exponential expansion continues, and these regions will always come to dominate the universe, however rare they may be, because they are exponentially expanding. Where inflation stops, big bangs herald the beginning of more sedately expanding regions like ours, but elsewhere, there is an ever-growing exponentially expanding universe, constantly spawning an infinity of big bangs. This theory, known as eternal inflation, leads to an infinite, immortal multiverse, growing fractal-like without end. This is truly mind-numbing, but we must emphasize that it is an entirely natural extension of standard inflationary cosmology. Eternal inflation opens up even more exciting possibilities. As we discussed above, one of the great mysteries in physics today is the origin of the constants of nature, such as the strength of gravity, the masses of the particles, and the value of dark energy. These values appear to be fine-tuned for the existence of life, and understanding where they come from is a prerequisite for understanding our existence. In eternal inflationary models, each mini-universe can have different values of these constants, and different effective laws of physics. The word effective is important. The idea is that there is some overarching framework out of which our laws and the constants of nature are selected randomly. If this is correct, then each of the infinite number of mini-universes that branch off the fractal inflationary multiverse can have different effective laws of physics, and all possible combinations will be realized somewhere. No matter how fine-tuned our laws appear for the existence of life, it is inevitable that such mini-universes as ours will exist, and there will be an infinite number of each possible set of combinations. There is no fine-tuning problem. Given the multiverse, we are inevitable. Yes, in isolation, the odds of you existing are almost vanishingly small. But given a mechanism for producing human beings, babies are born all the time, and their existence is not surprising. Here we have a mechanism for producing universes. And with an even greater statistical sledgehammer, the mechanism doesn't simply produce a few billion of them, it produces a potentially infinite number. This is a quite stunning theoretical model, and I understand that it sounds like wild speculation. It isn't, though. Inflation is probably correct in some form, in the sense that before what we call the Big Bang, there was an exponential expansion of space-time. Scalar fields, which are known to exist, have the correct properties to drive such an expansion, although there are other theoretical models of inflation as well. Theoretical physicists studying inflationary models have discovered that almost all of them are eternal, in the sense that they stop inflating in patches rather than all at once. This means that the potential for creating universes in the guise of inflation is always expanding faster than it is decaying away, and it will therefore never stop. We live in an infinite, eternal, fractal multiverse, comprised of an infinite number of universes like ours, alongside an infinite number of universes with different physical laws. We exist because it is inevitable. Almost.